Hi, I'm Brett Glencross, and in this lecture I'm going to talk to you about the advances in nutrition for tropical marine fish with an emphasis on Asian sea bass, or otherwise known as Barramundi. Biological systems are complex. When we try and look at the different factors that can influence the feeding process and the impact of nutrition, there's a range of things that we need to consider. The actual feed itself is one factor, but also things like the genetics of the animal, its behaviour and activity, the systems we're farming and the environment within all cause a range of interactions that actually make it sometimes difficult to actually undertake valid nutrition research that has meaningful application in the real world. So how do we deal with that complexity? Well, the modern way is to use models to actually allow us to deal with that. If we just take a look at this sort of diagram here to understand the old and the new approach, the old approach used to be to define a hypothesis, test the hypothesis at each level of organisation within a system, conduct the experiment, collect the results, compare it with the hypothesis, and then refine our process. And this process of empirical research rarely looked at look at one or two variables at once with any degree of surety. A modelling approach, we use a data on a whole range of organisational levels and develop an integrated model and use the model to actually construct a hypothesis. We then test that hypothesis by conducting an experiment, collect the results, and then compare those results with what the model suggested what was going on. And then we can use this to actually refine our model on a perpetual process. So we get a better assessment of basically a integrated biological system over time. Now, nutritional models for barramundi have been around for about a decade at least now. This is one that I published about 8 years ago. The advantage of these models is it allows us to look at the impacts of nutrition on the fish at a range of temperatures and a range of sizes, and with a range of different approaches to actually designing the feeds. But to give you a quick example of how this might be applied, say at 30 degrees, we look at a 100 gram fish that we can predict is going to grow about 2.88 grams a day. We know that the metabolic body weight exponent for a fish of that size at that temperature is going to be about 0.84, which means its metabolic body weight is going to be about 157 grams. That means its maintenance energy requirement is going to be about 7.4 kilojoules per day. A fish of that size, growing that 2.88 grams, needs to accumulate 19.14 kilojoules of energy. We also know that at that temperature and that size, the fish is about 61% efficient in energy deposition. Therefore, to accumulate that 19.14 kilojoules, it actually needs to eat 31.27 kilojoules. Therefore, the total energy demand is going to be the combination of that 31.27 plus the 7.4, meaning the fish will need 38.67 kilojoules per day to achieve that growth target. That same approach we can also use to estimate the requirements for protein, amino acids, and a range of other important nutrients in the diet. We can take that information and then use that to actually reverse engineer feeds as well. So for example, if we take 1,000 gram barramundi at 30 degrees, growing about 7.8 grams a day, we can predict that that fish will need about 160 kilojoules per day of energy. We can also predict that it will need about 3 grams of protein per day. Now, if we arbitrarily take a feed energy density of 18 kilojoules, it could be 16, it could be 20, but I'm just using 18. What we know is because the fish eats to an energy demand, that 160 kilojoules is satisfied by 18 kilojoules by 160 divided by 18, meaning the fish will need to eat 8.9 grams of that feed to meet its energy targets. That, because we know it's going to grow 7.8 grams and it's eating 8.9 grams, immediately we've predicted an FCR. That has also constrained the amount of feed the animal is going to eat. And therefore, if we know it needs this amount of protein and it's going to eat that amount of feed, then we can predict the concentration of protein required in the feed as well, 3 grams in the 8.9. The feed needed to have 34% digestible protein within the feed for it to be effective. That, what it shows is there's actually a close relationship between the energy demand and protein demand in terms of actually predicting how much protein the animal needs. In this case, you can see for this fish, it's about 19 grams per megajoule. Now, if we look at that 19 grams per megajoule, I'd actually argue that the requirement's not constant. One is that we notice that these requirements change continually through an animal's life. They vary with age, size, condition, but also the demands are not an exact estimate. What I would suggest is that across this transect of this line here, as we get a response like this, the red obviously is the peak value, and either side of it we have some room for latitude. Unless we go too far below it, then we start seeing basically the problems with nutrient supply. So how to apply this on a practical sense is to overshadow or overlay that red line with a series of formulations approximating that protein to energy ratio. So for example, in a 4mm pellet, that might be 50% protein, 16% lipid. But in a 10mm pellet, it might be a 40% protein and 26% lipid. So you can sort of see that we're getting into lower protein and higher fat diets as we go from small fish to large fish. Now, this application of using high energy diets in fish has already been tried in Australia quite well, where they're comparing for large fish, say 1 kilogram to 2 kilograms. We got much better performance with fish fed lower protein, high fat diets. They grew the same, just the FCR was a lot lower. About 0.15 decrease in FCR for every increase in 1 megajoule of digestible energy. Another recent observation or discovery is that we found out that Asian sea bass don't use starch very well. In diets that were formulated on an equal digestible energy basis, it was clear that they had a preference for using protein for energy. In fact, inclusion of starch seems to have a negative performance on protein utilization too. Some recent work that's been done with the University of Wageningen in the Netherlands on net energy models and comparing barramundi with carp has shown that basically barramundi don't derive any net energy value from starch. They basically almost get no net energy value from it. In fact, when we're looking at some molecular work that's been done, we can see that the animal actually down-regulates protein synthesis and up-regulates lipid synthesis in those animals that have had high levels of starch. So that observation of fatty livers and fatty viscera in Asian sea bass, well, it's probably largely to do with the starch content, and the starch is not adding much value to their energy intake. Some other recent work that's been done looking at phosphorus demands, by looking at increasing replacement of fish meals, we've identified that there's been a range of mineral sensitivities that have been identified. In fact, in this study here, we can see that high levels of low ash poultry protein concentrate led to poorer weight gain, which didn't make sense until they actually went and reformulated the diets through fortification with calcium hyperphosphate. And that resulted in better growth, better FCR, better calcium retention, but no change in phosphorus retention. But the fish certainly did a lot better. This suggests that phosphorus requirements are actually a lot higher than originally thought for Asian sea bass, probably certainly getting in excess of 1.5 to 2%. So raw materials are a perpetual problem. Obviously, with the rate at which aquaculture is growing, we need to increase our access to a range of raw materials. And one of the observations is that this is some of the recent data coming out of FAO. One of the recent observations is that marine fish are a big user of global fish meal reserves. In fact, marine fish globally now use more fish meal than salmon. The only thing that uses more fish meal than marine fish is shrimp. So there's a range of studies being developed now to actually try and improve our ability to use a range of raw materials to actually reduce our reliance on fish meal. However, in doing that, there's a traditional approach that we use for assessing nutritional effects of ingredients based upon the original review written about 15 years ago by Glencross, Booth and Allen. And that focuses on the characterisation, feed intake, functionality, utilisation and digestibility of the feeds by the fish with different ingredients in there to understand how they are impacting the fish. That review has recently been updated and upgraded. It largely covers some of those key issues, but also it now provides some examples of what happens when you don't follow the right approach, and also updating some additional needs for things like understanding immune function a bit more clearly as well. There's a range of data sources out there now that giving us a good overview of the characterisation and utilisation and digestibility, particularly of a range of different raw materials. This compendium was published about 3 years ago that pretty much consolidates all digestibility work out there for Asian sea bass. There's also been refinements in the methodology that we've been using to actually develop these assessments, and also some advances in technology on our ability to predict them in real time or very rapidly using modern methods like near-infrared spectroscopy. But you can see there's quite a substantial number of ingredients in this review that have been evaluated and have digestibility values for protein and energy, in some cases amino acids as well. That's allowed us to look at things like complete replacement, complete replacement of fish meal and fish oil in diets for sea bass. When we replaced fish oil, it had little impact on performance, except when the fish meal was at 0. Replacement of fish meal was a little bit more problematic. It was okay up until about 10%, and then we went over a cliff. What we were able to deduce from this is that these fish, they were reasonably large fish at start, 150 grams, that their requirements for a long-chain omega-3 are probably actually quite low, certainly lower than some other species we had thought. But it might be that if you satisfy their requirements when they're little, then they're a bit more tolerant when they're older. In this case, we were basically replacing the fish meal mostly with poultry meal and soybean meal, and the fish oil was replaced with rice bran oil. There's also been a lot of progress in understanding thresholds to essential fatty acids, EPA and DHA and arachidonic acid in diets for Asian sea bass. We've now got a good understanding of where those thresholds are for fish of different size. We can sort of see that once you go over a threshold, though, that the animal does, but you do start to impinge performance quite significantly, and those effects can be seen very quickly, like within weeks, and it does lead to a range of physical abnormalities when you have very, very low levels. We have improved our ability to use alternative oils, things like rapeseed oil, or in this case, poultry fat. The use of poultry fat in diets for Asian sea bass was shown to not have any impact on performance at all. So complete replacement of fish oil with poultry oil maintained the same growth and the same FCR, but there was some significant differences in carcass and fillet fatty acids. In fact, what we saw is when we used the fish oil replacement with poultry oil, we ended up with the same fat levels in the meat, but there was an increase in monounsaturates and a 3-fold reduction in omega-3. But this reduction was non-linear, which supports the notion of selective retention of LC-PUFA, which suggests that there's preferential use of monounsaturates and saturates. We've also done other work looking at showing that there's saturates are really poorly digested by this species. So you need to be careful if you're using, say, oils like tallow or something, or palm oil. So that's a bit of a quick summary for where we're at with some of the progress being made in the last 5 years on Asian sea bass nutrition. There's been substantial progress made in defining requirements for a range of different areas, and some new insights have emerged. Modelling is now proving to be a really useful tool to explore new ideas and concepts, and our ability to actually understand how we apply different nutritional strategies across different environments and different genotypes and so on. There's also accumulating evidence that shows that including starch in the diet is problematic. If you want a fish to have a high fat loading, then starch is a good way to do it, but we might need to rethink the way in which we look at the feed manufacturing process if we're going to get rid of starch. There's certainly evidence that basically if we get rid of starch, there's better growth of the fish. And revisiting phosphorus requirements has shown that for Asian sea bass, phosphorus demands are substantially higher than previously thought. So we need to be mindful of that. The fish meal and fish oil story, there's a range of considerations there. There's a range of publicly available databases that are now available that have value, it's on ingredient value. There's clear thresholds of palatability when we remove things like fish meal. And there's also clear thresholds for essential fatty acid requirements that we need to consider if we're taking fish oil out as well. And notably, both of these seem to impact on the qualities of the fish meat. And with that, thank you, and hope to see you in Singapore in 2021.